Hello everyone, I am Mostafa Salah, an assistant professor at the Electrical Engineering Department at Future University in Egypt. I will present the paper titled Simulation and Optimization of Highly Efficacious Polymer Solar Cell. The rest of authors are Dr. Mohamed Mousa, Engineer Ahmed Mostafa, Engineer Mohamed Senary, Engineer Youssef Mohamed, and Dr. Mohamed Hamouda. The presentation contents are firstly the polymer materials, secondly the proposed solar cell structure, after that the simulation setup, then the optimization of the proposed cell, after that the results summary, NIP structure, state of the art, and finally the references. The polymer solar cells. Polymer photovoltaics have a wide band gap. This creates an opportunity in pairing them up with low band gap photovoltaic technologies. The polymer materials have a lot of advantages like tunable band gap, low cost, ease manufacturing, efficient flexibility, lightweight, and sustainability. So the proposed solar cell structure is uh, front contact of ITO, whole transport layer of P.PSS, P, PDPT, and PZT polymer blend is used as an absorber layer. The electron transport layer is PFNBR. Finally, the back contact is the AG. The incident light from the front contact is AM 1.5, which is the air mass 1.5 global spectrum. The simulation setup. All simulations are done using SCAPS, one-dimensional, with a temperature of 300 Kelvin. The contact's characteristics are for the left contact or the back contact, EG is used with 4.1 electron volt work function and SN 10 power 5 centimeter per second and SP 10 power 7 centimeter per second. For the right contact or the front contact, ITO is used with 4.7 work function electron volt, 10 power 7 SN, and 10 power 5 SP of centimeter per second. The used layers parameters in this table are proposed. Firstly, the electron transport layer has a thickness of 5 nanometer. The energy gap is 3 electron volt. The affinity is 3.9 electron volt. The relative permittivity is 3.5. The conduction and valence bands densities NC and NV are 10 power 21 per centimeter cube. The electron mobility is 10 power negative 4. The hole mobility is 10 power negative 6, which is low. The acceptor concentration is 0 in the electron transport layer. The whole transport layer thickness is 43 nanometer. The energy gap is 1.3 electron volt. The affinity is 3.6 electron volt. The relative permittivity 3.5. The conduction, the valence bands densities are the same for all layers. The electron and hole mobilities are 8 times 10 power negative 4. The acceptor concentration is 9.2 times 10 power 18. Finally, the polymer layer or the absorber layer thickness is 100 nanometer. The energy gap 1.61. The affinity is 3.69. The relative permittivity is 3. The electron mobility is 5.1 times 10 power negative 4. The hole mobility is 2.5 times 10 power negative 4 without a doping. This simulation setup is used and calibrated with an experimental work in reference 12 to validate our model and the materials parameters. The results of this cell using SCAPS 1D, the JV curve, the green curve is extracted from the simulation, and the black curve is from the experimental work. Also, the quantum efficiency, which is the external quantum efficiency, is compared in this figure. To conclude the output performance parameters, the fill factor of the simulation is 68.45 versus the experimental is 68.5. The short circuit current density is 23.9 milliampere per centimeter square for both the simulation and the experimental work. The open circuit voltage is 0.91 for both simulation and experimental work. The power conversion efficiency of the simulation is 14.91 and for the experimental is 14.9. So the used model and the materials parameters are very good to simulate the proposed cell. To increase the efficiency, we will optimize this cell, starting by optimizing the electron transport layer affinity. We studied the electron transport layer affinity from 3.4 to 4.5 electron volt. The highest power conversion efficiency is achieved at 3.82 electron volt, which yields a maximum eta of 15.3%. So we proposed different materials to replace the electron transport layer, which was PFNBR. We proposed zinc oxide 0.3, sulfide 0.7, WO3, zinc oxide, zinc oxysulfide, because these materials have affinity close to the required, which was 3.82. So we used these materials and compared the results. The power conversion efficiency of the calibration was 14.91. When we used the zinc 0.3 S 0.7, the power conversion efficiency increased to 16.2. When we used WO3, it was 15.28. Zinc oxide has 15.12, and finally, zinc oxysulfide based polymer cell has a power conversion efficiency of 14.70. So the ZNO 0.3 S 0.7 has the highest efficiency. We can expect these results from the materials parameters. For this material and this material, the electron affinity is 3.8, which is very close to the optimum for this cell, which was 3.82. ZNO 0.3 S 0.7 is better than WO3 because the mobility of the electrons is higher than 3 times of the WO3, which is 100 versus 30. And also the mobility of holes is 25 versus 20. After that, we studied the impact of the back and front contact work functions. So we started by the impact of the back contact work function. The highest power conversion efficiency was 17.27 when we used the work function of the back contact of 3.7 electron volt. For the front contact, the highest eta was 19.52 and it is achieved at 5.2 electron volt for the work function of the front contact. The HTL has has a significant impact on the performance. So we studied the thickness of the HTL. Increasing this thickness increased the performance. At this high thickness, the whole transport layer is used as an absorber layer. So the cell is has a double absorbers, which explains the performance enhancement. The best behavior is achieved when the thickness of the HTL is 10 micrometer with an eta of 31.58%, which increased by 12%. The impact of the absorber thickness, which was the polymer layer, the optimum behavior is achieved when the thickness of the absorber layer is 74 nanometer with the highest eta of 31.67. The impact of the ETL thickness is very low, but we choose 1 nanometer with eta of 31.97. The impact of the polymer bulk defects density has a significant impact on the performance. Decreasing the total defect density in the bulk of the absorber layer, of course, will increase the performance. So we choose 10 power 9 to be an experimental value for this, and we can increase it to 10 power 11. The eta at 10 power 9 per centimeter cubed defect density results to a eta of 33.04%. Result summary: the calibrated polymer solar cell started with eta of 14.91. After the optimization and electron transport layer material selection, we achieved a performance the highest performance with eta of 33.04. After that, we studied the inverted structure. The default for this cell is PIN. When we investigated the inverted structure, which is NIP, the eta is achieved 44.48%. Finally, the state-of-the-art comparison for this cell with different active blend and different ATLs are proposed, which provide and highlight our impact to this cell performance. We achieved 33% for the PIN structure and 44 for the inverted structure. Finally, the references. Thank you. For any questions, you can contact me by email or by WhatsApp. Thank you.